Next up, we have Karthik Senthil, who is a master student at PPL. He's going to be talking about a union find library implemented on top of Charm++ and its uses.
All right. Good evening, everyone. I've always considered giving the last talk for the day to be the hardest task, particularly when you know that you are the final speaker between the listeners and an amazing banquet waiting for them right across the building. So I'll try keeping this as interesting as possible. I'm Karthik, a first-year graduate student at the Parallel Programming Lab, and I'm here to present our active ongoing research in developing a parallel union find library in Charm++. So firstly, the problem statement. This is a definition borrowed straight from Wikipedia. A union find algorithm is an implementation of any algorithm that performs two basic operations on a disjoint set data structure. So a disjoint set data structure is a data structure in which your elements can be partitioned into unique subsets. So the first operation, called the find, helps to determine which particular subset an element belongs to. And your second operation, union, combines or joins two subsets in order to form a larger subset. One of the most common applications that uses union find algorithm underneath is the connected components detection in a graph. This application is the cornerstone of various practical use cases and is widely used in various fields of science and technology. The concentration of our library is to perform connected component detection in very large-scale graphs using union find algorithm. So the other applications which use union find algorithm include the Kruskal's minimum spanning tree construction, various network connectivity problem, etc. So this will be the brief outline of the remaining of my talk, where I'll be focusing on how we designed and developed this library to perform union find algorithm in Charm++. So firstly, the related work. Connectivity in a graph is a very well explored and a very well solved problem. I'm very confident that even today, if I decide to write a report titled Learning Connected Component Detection in a Graph, my bibliography section will be much longer than my main content. So here are the top 4 results that are very relevant to the problem that we're trying to solve. So first up is the work done by Shilowak and Vishkin, a very famous, highly cited work where they develop an order of log n based parallel connectivity algorithm. The second work by Nasimi and Sartaj Sahini is again a very well cited work where they develop a connected component detection algorithm for a mesh based parallel computer. The third work by Professor Krishnamurthy and Professor Steve Lametta from Illinois is a work where they develop connected component detection on a distributed memory machine. It is interesting that they used the work of Shilowak and Vishkin and applied some sequential algorithms to extend the connectivity detection algorithm to a distributed machine. One of the more recent works is by Professor Mane, where he develops a scalable parallel union find algorithm for distributed memory, where they optimize specifically the find operations. So what we did notice was that most of the recent work and optimizations were targeting shared memory architectures and which were not very scalable for very large scale graphs on a distributed machine. So our primary motivation is to develop a generic, highly scalable union find algorithm for a distributed asynchronous environment. By highly scalable, we are talking about graphs that scale beyond the hundreds and thousands of nodes of a machine like Blue Waters. So what is the Charm++ approach to solving the union find problem? Consider a graph G containing n vertices and m edges. A given edge connecting vertex V1 and V2 represents a union operation. So in our algorithm, we first message vertex 1 in order to perform the find operation of vertex 1 and identify which component this vertex 1 belongs to. Each component is identified by a unique element within the component, which we call as the boss of the component. So after finding boss 1, we ask boss 1 to message the vertex 2 in order to perform the find operation on vertex 2 and find the boss 2. Now that we have both bosses, we just need to realign their parent pointers based on some criteria like size or your depth of your tree, etc. So what we are effectively doing here is we are asynchronously building a forest of inverted trees where each tree represents a unique connected component and the root of your tree is the representative element of your component. So this is the graphical representation of our algorithm where we show how the union operation between vertices A and B is performed. So you can see that vertex A initiates the find operation, finds its boss. That boss messages vertex B and performs the find operation. We use a very simple policy stating that boss 2 always points to boss 1 irrespective of any condition. Of course, this policy can be always changed as long as we collect enough information during our find operation. So what were the challenges that we faced while implementing this design of our algorithm? Asynchronous environment or asynchronous execution brings with it a bunch of race condition problems. And our biggest challenge was to prevent the formation of cycles in your asynchronous tree construction. So consider this simple triangular graph containing 3 vertices, 3 edges, and each vertex on a different char on an independent PE. So let's say that your first char receives a union operation between vertex 1 and vertex 2. So this is going to make your vertex 2 point to vertex 1. At the same time, your second char is going to get a union request between vertex 2 and vertex 3, which makes vertex 3 point to vertex 2. And simultaneously, your third char is also going to get a union request between vertex 3 and vertex 1, which makes vertex 1 point to vertex 3, though you intuitively know that vertex 1 is the root of your tree. So this is a very hard problem to break because there is just too much symmetry and a lot of asynchrony and independence. We tried a lot of techniques like locking, like tagging your messages, but nothing seemed to solve the problem efficiently and give us the correct results. And that is when we realized simplicity is the best way to solve any, to deal with complexity. We enforce a strict ordering in your union operation, say based on your vertex ID. So only a higher ID vertex can point to a vertex with a lower ID. What this effectively means that you're bringing in an additional min heap like property to the trees that are constructing, and the root of your tree is going to contain the lowest ID vertex in your component. So now it is easy to detect a possible cycle edge in your tree construction. This is because if a lower ID vertex is being asked to a higher ID vertex, it means that it is a possible cycle edge or a back edge. And in order to comply with our strict ordering policy, we reprocess this request by flipping the order of the request. So we have three important functions which form the core of the entire algorithm. The first one is called union request between two vertices v1 and v2. First, we perform the order check in order to comply with the strict ordering policy. If it is invalid, you flip the operation and reprocess the request. Otherwise, you perform the find operation on the vertex 1, which we call find boss 1. Find boss 1 is a standard find operation where if the requested vertex is the root of the tree, you initiate the find operation on the vertex 2. Else, you perform the find operation on your parents and hierarchically climb your tree path. Find boss 2 is very similar to find boss 1, except an additional check on the ordering to ensure that we stick to a strict ordering policy that we state in the previous slide. So after performing some initial runs with this implementation, we realized that we need a lot of optimizations in our current implementation. So what we did notice was that tree construction phase is very communication intensive. To just give you a rough estimate, we were creating about 1.5 billion tiny messages for just a 16 million vertices graph. We also found the trees to be very deep, which is not unnatural for any union find algorithm. But remember that these trees are spanning across multiple chars and across multiple Ps across various nodes. So each time a fresh union request comes in, your tree climbing process is going to become very costly, and that's going to slow down your entire tree construction phase. So this motivated us to perform two critical optimizations. The first one is what we call as locality-based tree climbing. So what we do here is we ask the char to sequentially traverse the path until it knows that the next vertex on the path is outside the char. This technically increases the amount of sequential work that your char is doing, but this drastically reduces the number of messages that is being sent to the runtime system. In fact, with just this optimization, we were able to observe a 25x speed up in our tree construction phase. The second optimization is what we call as local path compression. Path compression is a very common technique that is even used in the sequential union find algorithm. But what we do here is that before the char messages another char outside for the next vertex, we realign the parent pointers of all the remaining nodes on the same tree path within the char to point to the pseudo local boss. So what you're effectively doing is you're building a shallow tree within your char, and sometimes this gives you one-hop access to your bosses if your entire tree is within the same char. Of course, these optimizations are more meaningful and are more promising if we extend to PE level or node level, and that's on our cards for the future work of this library. So what is the current status of our implementation? We have designed this library using the bound array concept in Charm++. We have generalized the entire library using templates, so any generic graph application that you develop in Charm++ can use this library. The connected components detection module has been integrated into the library, so this has three phases. In your first phase, you build your forest of inverted trees using our asynchronous union find algorithm. In your second phase, you identify the boss of each component and label all the vertices in the component with the correct component ID. In your third phase, you perform some pruning operation on your components to prune out any insignificant components. We have tested and verified this implementation with various real-world graphs, basically protein structures that we borrowed from the protein data bank. And we are also performing large-scale testing as I speak on various supercomputers with the probabilistic mesh concept. So probabilistic mesh is an idea borrowed from cluster dynamics and computational physics. The idea is to build a random graph on an underlying lattice structure. So each point in your lattice represents a vertex, and you say that an edge exists between two lattice points based on a probability. This probability value is calculated based on the lattice point's coordinates, and if this probability is greater than a threshold, you will say that an edge exists between these two lattice points. So what are the advantages of using probabilistic mesh? Well, I can easily scale my size of the graph. All I need to provide is a mesh size. I don't have to provide any vertex information or edge information. Second, it is easy to verify my results and catch any race conditions. This is because if I fix my probability and my mesh size, I'm bound to get the same graph with the same number of edges and the same number of components. So now I can easily play with the number of chars and number of PEs and change my execution and make sure that I'm getting the same results in each run. So we performed some basic experiments to evaluate our library. The first experiment is where we wanted to evaluate the runtime of the different phases in the connected component detection. We used 4 different mesh configurations, starting at 1 million vertices and scaling that all the way up to 64 million vertices. We used 3 different probability values, 0%, 40%, and 60% probability. So 0% means that there are no absolutely any edges in your lattice, so meaning each vertex is a component by itself. We also fixed the problem size in a chart to a 64 by 64 mesh piece. The second experiment that we performed was a scaling performance evaluation. Here we fix the mesh configuration at a fixed size of 4 million vertices for 40% probability. We chose a rather small problem size per char at across for just 2 cross 2 mesh piece, or just 4 vertices per char. And we also scaled the number of physical nodes from 2 to 64 nodes. All these experiments are performed on the Stampede KNL cluster. So this is the result for the phase runtime evaluation for 1 million vertices on 2 nodes of Stampede. So here you can see the 3 different phases stacked on top of each other to tell you how much execution time each phase took. So the purple phase represents the phase 1, or the tree construction phase. You can see that this phase is progressively increasing with probability. This is because as you increase the probability, the number of union requests or the number of edges in your graph is increasing. So you spend more time in your traversals and performing union requests. The green portion represents almost an insignificant part of your execution. This is because the green portion represents your labeling of components in different vertices, and this phase is completely asynchronous and happens in parallel. So there is not much time being spent in this phase. The third phase, which is the more interesting phase, is where we prune out components. So this is like a bookkeeping phase where you need to collect counts of vertices from each component, make a map saying component A has X vertices, component B has Y vertices, and transfer that information to different vertices to tell them if they need to be pruned or not. So we implemented this phase with an algorithm which depends on the number of PEs that you're using and as well the number of components in your graph. So for the first case where you have the highest number of components, most of your execution time is being spent in just this bookkeeping phase. We observed a similar trend for the 4 million vertices graph, and our execution time was hitting up to 15 seconds for the 0 probability case. The more interesting result was for the 16 million vertices graph on 16 nodes of Stampede. So what we observe here is an entire reversal of roles. Your phase 1 is now taking much more portion of your execution than the remaining phases. So what happened here was not only did your problem size increase, but also your communication overhead started increasing. For my larger problem size, the number of chars in my system is greatly going to increase, and my messaging is now across multiple nodes and multiple PEs, and this overhead is kicking in your execution. Also, your trees across different chars are becoming much deeper and much longer, and every tree climbing path every tree climbing phase is becoming costly in the phase 1. So this result kind of pointed out to us that phase 1 is the critical bottleneck for very large scale graphs that we want to target, and we are working on a lot of optimizations for targeting this phase alone. We observed a very similar result for the 64 million vertices graph, which was the largest experiment that we performed, and we were hitting about an average of 175 seconds in execution for the entire algorithm. So the results for the scaling performance is given here. We just wanted to evaluate how different phases reacted for increasing the number of computational units. On the x-axis, we plotted the number of physical nodes, and on y-axis the execution time. So you can see that as I increase the number of nodes, my execution time in phase 1 is decreasing as expected until I reach a point like say 32 nodes, at which point you can notice that the problem has run out of enough parallelism to execute. This is because it's a very small problem size, and beyond 32 nodes, we do not have enough parallelism to exploit within Chum++ itself. A similar trend was observed for the phase 2. And for phase 3, we see a linear increase in runtime. This is what I stated before. This phase 3 depends on the number of PEs that you're using. And as I increase my number of PEs, my execution time for this phase also increases linearly. So what's in store for the Union Find library? There's a lot of exciting work happening here. We have scope for many great optimizations. So firstly, we want to target optimizing phase 1, as we noticed that it is the critical bottleneck for very large-scale graphs. So we're planning on something like sub-phase approach and various PE and node level aware optimizations. We also want to test out priority for particular kind of messages and see how different subclasses of graphs react to this optimization. Of course, we want to implement a global level path compression and build a shallow tree not just at your char level, but also at your PE level and node level. We also plan on integrating the TRAM library, which is the topology-aware routing and aggregation of messages from Charm++, since this is a very communication-intensive application. We also plan on targeting Changa to perform the friends of friends-based galaxy detection component. So the code and examples for this work is available online. Thank you. Any questions?
Well, you didn't check the program since you prepared your talk. There is one more after this, so no banquet just yet.
I'm sorry.
So maybe you're addressing this a little bit, but one issue with union finding is sort of the equivalent of load imbalance, right? So existing cosmological group finders do very well if you've got disconnected sets distributed through your volume. They almost all fail miserably if you have sort of one large set that is, spans many processors and then not much in the rest. So have you, have you compared sort of this one large group versus many small groups and how your algorithm scales
yes, that is
in
something
each
that I
case?
need to explore, because right now all my performance or tests that I've showed you, it's just very, very equally distributed load across multiple chars or multiple nodes. But I think we're going to be relying a lot on the Charm++ runtime's load balancing framework itself more. But we will be looking into any possible optimizations by integrating load balancing into the library itself.
Thank you.
Any more questions? Let's thank the speaker. Thank you.